Hello everybody and welcome. This is To The Point Learning, and this is the first video in a 10-part series covering everything we need to know for the AQA 9-1 GCSE Chemistry course. And in this video we're going to be going over the topics of atomic structure and the periodic table. So without further ado, let's get started. So the first section is atoms. Now the word atom is in fact Greek for can't be divided. So if you were to take an element and cut it up into smaller and smaller pieces each time, you'd be left with the atom. Now that fits in nicely that the first bit of information we need to take note of is that the atom is the smallest part of an element that can exist. You can't get any smaller than an atom. Now, atoms of each element are displayed on the periodic table by their chemical symbol. And below here I've attached a copy of the periodic table that you will in fact get in every one of your AQA GCSE science exams. This is the exact periodic table you will get, so make sure to become familiar with this to save any last minute panic when it comes to the exam. We also need to know here that there's about 100 different atoms known, and these are all represented here on this periodic table. Now, if we isolate one of the elements from the periodic table, we will get its nuclear symbol. So, for example, here we have the nuclear symbol for sodium. And you'll notice it has three sections to it. It has its chemical symbol here, so for sodium it's Na, which just identifies what the atom is. But we also have two numbers. A larger number up here and a smaller number up here. Now to explain these, we need to be familiar that an atom is in fact made up of three subatomic particles: the proton, the neutron, and the electron. And these numbers, the 23 and the 11 for sodium, tell us about the number of these three subatomic particles in that atom. So the first number here, the number 23, is called the atomic mass number, and this identifies the number of protons and neutrons in an atom of sodium. And the smaller number, so 11 for sodium, identifies the number of protons in an atom of sodium. So using these two bits of information here, we can work out that for sodium, the number of protons is therefore 11, its atomic number, and the number of neutrons can be calculated from a simple subtraction by subtracting the atomic mass number from the atomic number, leaving us with the number of neutrons, which in sodium's case is 12. But to work out the number of electrons, we need to know a little bit more. We need to know that the number of protons in any atom on the periodic table is equal to the number of electrons. So therefore, in sodium's case, it has 11 electrons. So make sure to become familiar with how you calculate the number of subatomic particles in an atom from the periodic table. Now the next section is isotopes. Now before we go any further into what an isotope is, we need to be familiar with the following: that the number of protons dictates the species of atoms. So if I have two atoms and they both have the same atomic number, they are by definition the same atom because they have the same number of protons. Whereas if they have a different atomic number, they are therefore, by this definition here, different atoms. Now that may seem obvious, but let's look at the following. Atoms of the same element can have different number of neutrons, and these atoms are called isotopes. Now, a common example of this is chlorine. You may be familiar that chlorine on the periodic table has an atomic mass number of 35.5. And this is because there are two common isotopes of chlorine found on our Earth: chlorine 35 and chlorine 37. Now note here that these are in fact the same element because they have the same atomic number, so the same number of protons, but they do in fact have different atomic mass numbers, 35 and 37 respectively. And both of these isotopes are common for chlorine and have different abundances. So chlorine 35 has an abundance of 75%, whilst chlorine 37 has an abundance of 25%. So to calculate the relative atomic mass that is displayed on the periodic table, so here 35.5 for chlorine, we need to calculate an average of these two numbers, a weighted average that takes into account their respective abundances. So to do that, we need to do the following. So this is the calculation we do. 35 multiplied by its relative abundance, add that with chlorine 37's relative abundance, divide by 100%, and what we will be left with is 35.5, which is in fact the relative atomic mass that is shown on the periodic table. And the reason behind that is because of this isotopes. So become familiar with this. So the next section we need to become familiar with is atomic structure. So if we were to take an atom and look at it under the microscope, we would have the following. What we should observe is that there is a central nucleus and a series of energy levels or shells. Now we need to know that in the nucleus, the central nucleus of the atom, this is the home of two subatomic particles, the proton and the neutron, whilst the energy levels, or the shells, contain the electrons. So with electrons and how they fill up in energy levels, they will always occupy the lowest possible energy level, and electrons will fill up shells in this following order. So the first shell only has space for 2 electrons, the next shell has space for 8 electrons, and so on. So from there on after, you only have space for 8 electrons on each shell. So if we have an atom with 12 electrons, the first 2 electrons will sit on the first energy level, then the next 8 will fit on the further out energy level, and the final 2 electrons will sit on the third energy level. And that will be the electronic structure of an atom with 12 electrons. Now, before we go any further, we do need to be familiar with two following things: the relative radius of a nucleus and the relative radius of the whole atom. So the radius of the nucleus, the central part, is in the order of magnitude of about 1 × 10 to the minus 14 meters, whereas the radius of the whole atom is in the order of magnitude of about 1 × 10 to the minus 10 meters. Try to become familiar with these two numbers here because they are quoted in your specification, but basically all this is saying is that the nucleus is very small in comparison to the size of the whole atom. Okay? And the final thing we need to know about this is a little bit more information about the 3 subatomic particles: the proton, the neutron, and the electron. And we need to know stuff about their relative mass and their charge. So the proton and the neutron both have the same relative mass of 1, whereas the electron has a negligible mass in comparison of about 1/2000th that of a proton or a neutron. And seeing these two bits of information here, we can clearly see that most of the mass of the atom is in the nucleus area, since the proton and the neutron both have the biggest relative mass. We also need to know a little bit about the charge. So proton here has a positive charge, neutron has no overall charge, and the electron has a negative charge. So make sure to become familiar with the contents of this table and the structure of the atom, as this will definitely come up in your exam. So the next stage is the development of the atomic model. The atomic model hasn't been as it was shown on the previous slide throughout history. And the bottom line of this slide that we need to make sure we are familiar with is that new evidence leads to scientific model changes or adaptations. So that can be new evidence, new discoveries, new ideas, etc. So we're just going to go over the brief history of how the atomic model has been adapted over time with new evidence and new ideas, etc. So initially, before the electron was discovered, atoms were thought of as tiny solid spheres, and that was it. They were just thought to be solid spheres. But then the electron was discovered, and this led to the adaptation of this model here to the plum pudding model, which was the same solid spheres but with pockets of negative charge, like a plum pudding model. But then further experiments from the alpha particle scattering experiment led to the conclusion that the mass of the atom was concentrated at the center in a nucleus, and that was charged. And the nuclear model, then, that we've seen in the previous slide, was changed and adapted. And then further information from Bohr, discoveries from Bohr, adapted this nuclear models to where electrons were orbiting the nucleus at specific distances. So the model was further adapted. And then finally we had Chadwick, which discovered neutrons, and he adapted this model even further to what we're familiar with on the previous slide. So this whole here, this thing is just, this bottom line is what we need to become familiar with, is that new evidence and discoveries lead to scientific model changes, as shown here. So moving on, how is the periodic table arranged? Well, the periodic table is arranged in order of increasing atomic number, so increasing number of protons. But how is this arranged? So it in fact reads from left to right. So the smallest atom is hydrogen, and then we read from the left to the right. So then the next biggest is therefore helium, and then going on from there we drop a row and we start reading from here. So the next biggest is lithium, then beryllium, etc., etc., reading from left to right, and this is in order of increasing atomic number. But another interesting thing about the periodic table is that it is arranged in order of groups. So you'll see across here that there's a series of numbers, and these are called groups. And what these groups tell us is the number of electrons on the outermost shell. So for example, any atom in group 5 has 5 electrons on its outermost shell. And the only difference as you progress down the groups, so the difference between nitrogen and phosphorus, is that phosphorus here has just an extra energy level, an extra shell of electrons, and that's the difference. So as you progress down, the atoms become bigger. But similarly to the development of the atomic model, the periodic table hasn't been as we are familiar with today, because we didn't know everything that we know now back then. And this was similar to what one of the periodic tables looked like, but even more dated one would have looked further different to this, and this is because they were arranged in order of atomic weight, which is in fact different to atomic number. This is atomic mass number. But back then, not every element had been discovered. So the periodic table wasn't in fact periodic. It didn't show periodicity. So then came on another scientist who recognized this issue, Mendeleev, and he ordered the elements in groups that had similar properties, so it satisfied periodicity, so it showed periodicity. But in order to overcome the issue that not every element had been discovered, so this ordering in order of atomic weight wouldn't show periodicity, he left gaps. So he left gaps for undiscovered elements so that periodicity was consistent and so that the periodic table was in fact periodic. And then later on, the undiscovered elements that he left gaps for were later discovered and then fulfilled his expectations of where they should be. So further developing his model and giving it more confidence. So this idea of the development of the periodic table is similar to the development of the atomic model, just that new evidence, new ideas brings to the table new developments of what's there. So become familiar with this. So the next section we need to cover is that of compounds and mixtures. So we need to know the definition of a compound and that of a mixture. So a compound is where elements are chemically combined through bonds, whereas a mixture is where elements or compounds are not chemically combined. And therefore, mixtures can be separated through physical processes, and a few examples of physical processes are here: distillation, filtration, and crystallization. So become familiar with these two definitions here, and then you'll be set. Now, before we move on to any of the latter slides, we need to become familiar with the following: that atomic structure is indicative of the reactive properties of an element. So, a good way to understand this is that atoms will always seek stability, and an atom's definition of stability is in having a full outer shell of electrons. So just like humans will seek stability in their finances and in their health, atoms will seek stability in the form of a full outer shell of electrons. And this can be achieved through chemical bonding, in where electrons are shared, lost, or gained. So, for example, metals. Metals are to the left of the periodic table, so they occupy the lower groups, so they have fewer electrons in their outer shell. So they tend to achieve stability, a full outer shell, by losing these outermost electrons and exposing a lower full outer shell of electrons. So therefore they've achieved stability in losing electrons. And they do this because they are further away from the nucleus. Those outermost electrons are further away from the nucleus compared to elements to the right of the periodic table. So there's a weaker attractive force from the positive nucleus, and it's easier, more energetically favourable for them to lose those electrons, to expose a lower, more full outer shell of electrons. But in comparison, the non-metals, which are to the right of the periodic table, they have a lot of electrons to remove, so they tend to gain electrons to achieve stability. And the reason for this is that they are closer to the nucleus. The outermost shell is closer to the nucleus, so there's stronger attractive forces between the outermost electrons and the nucleus. So it's not, in fact, energetically favourable for them to lose electrons. So the next section is transition metals. Now the transition metals occupy kind of the middle section of the periodic table. And you need to be familiar with the following transition metals, just to be able to use in your answer and know that these are transition metals. So chromium, manganese, iron, cobalt, nickel, and copper. Now, as we said, they're located at the center of the periodic table, and they have typical metal properties, so that they're hard and dense, and they can also be molded into different shapes, so good for building materials, etc. Now, because they're metals, they're right in the middle of the periodic table, it's neither energetically favourable sometimes for them to gain or lose electrons, so they sometimes do a mixture of both. So that's why they form more than one ion. Sometimes they will lose electrons to form positive ions, but sometimes they'll gain electrons to form negative ions. So generally you'll see a collection of ions that are available for the transition metals. Another property of the transition metals is that because of this, they can form very colourful compounds, and this is related to its electronic structure, but you don't really need to know why, you just need to know that they can form very colourful compounds. Now, the next bit is the catalysts. So catalysts are something that help improve the speed, the rate of a reaction, and metals are very good at this. The transition metals form the basis of great catalysts. So there we go, that's what we need to know for that section. So the first group we're going to come in contact with is group 0, and these are called the noble gases. And group 0 elements are listed here, so helium, neon, argon, etc. And they each have a full outer shell of electrons. So 8 electrons in their outer shell, except helium, which has 2, and that's because the first energy level, electron shell, can only capacitate 2, so technically helium still has a full outer shell, which is why it's included in group 0. Now, all of these noble gases are energetically stable because they have a full outer shell of electrons, so therefore they're very unreactive, because there's no need to gain, lose, or share electrons to achieve stability, because they've already got it. And as a result of this, they exist as monatomic molecules, which is just single atoms which are not bonded together at all. And therefore, because they're so energetically stable, they're often colourless, non-flammable gases. They just exist. They don't really engage in much reaction at all. The one thing we do need to know with group 0 is that as you progress down the group, the boiling point will increase. So it will require more energy to boil it. And this is because as you progress down the group, the molecule, the atoms, will become bigger. Therefore, they have a more positive nucleus simply because they have more protons. And when there's more charge involved, the intermolecular forces between two different noble gas molecules will become stronger, because when it's more positive and more electrons are attracting together, there'll be a stronger force, and therefore there's more energy to break apart these molecules and change the state of it. So hence they have higher boiling points as you progress down the group. Now the next group we're coming into is group 1, which is the alkali metals. And the alkali metals are listed here. So we have lithium, sodium and potassium as the first three. And group 1 are essentially the opposite of group 0. They only have one electron on their outermost shell, which means that they are very, very reactive, but also they have properties of being quite soft and a low density. So make sure you become familiar with this, because that will be handy in your exam. And we also need to know that they do react, so because they're very reactive, we need to be familiar with the following equations. The reaction with water, which I've listed here, which the alkali metal in question will form a hydroxide and hydrogen when it reacts with water. We also need to be familiar with its reaction with chlorine, and both of these reactions are stated on the specification, so I would just suggest taking a look and note and understanding these equations, and go into your exam being familiar with these to not get stumped on them. And the final thing is, you don't need to know a reaction for this, but they will react with oxygen, and you need to know that for the first three elements, so lithium, sodium and potassium, they'll form these compounds with oxygen. So just try and memorize these, and that will put you in good stead for your exam. Now the final group we're going to look at is group 7, and you may already guess these are called halogens, and because they're in group 7 they have 7 outermost electrons. Okay, and here's a list of the halogens. We've got fluorine, chlorine and bromine as the first three, and these are non-metals because they're to the right of the periodic table, and they exist as diatomic molecules, so they come in pairs. So if you see chlorine, it will be 2 chlorine atoms bonded together, and that will be how it will exist in our atmosphere. And these will often react with metals to form ionic compounds. So because they only need one more electron on their outer shell to achieve stability, they will gain this electron to form an ion. But they'll also react with non-metals to form simple molecular compounds. So we need to be familiar with the following, and we will go on in later lessons to the details on ionic and simple molecular compounds, but not for now. We just need to know that. And the properties we need to know is that as you progress down the group, they become less reactive, and this is because they're further away from the nucleus, so it's harder for them to gain that extra electron because the positive charge is further away, so it's not as strong. But they have a higher melting point as you progress down, so same as the group 0 has a higher boiling point, higher melting point, boiling point, same thing essentially, just different changes of state, and that increases down the group for the same reasons: larger in size, stronger forces, etc. And that's because of the higher relative atomic mass, etc. So moving on, we have to look at halogens and how they interact in displacement reactions. And before we go into the displacement reactions, I've included from the previous slide the list of the halogens, and we do remember from the previous slide that as you progress up the group, they become more reactive, and that's important for displacement reactions. So here we have chlorine reacting with potassium iodide. So we've got 2 halogens, one in compound and one not in compound. Now chlorine, which isn't in compound here, is more reactive than iodine. So as a result of this, it is going to displace the iodine compound. So here we have, on the product side, we have chlorine in a compound and iodine on its own, and that is because chlorine is more reactive, it's higher in the series, so it will displace the iodine compound. So just to clarify this a bit further, here we have chlorine again, but reacting with a compound of bromine, and because bromine is lower in the group, it is less reactive. Chlorine will therefore displace that also from its compound, and therefore we have the product there. So just become familiar with that Displacement reactions. The more reactive halogen will displace the less reactive halogen from its compound.